Hey guys, welcome back to another video. So in this video, we'll be talking about resonance structures and sort of how they're associated with Lewis structures that we already know. So resonance is basically a phenomenon that we see when like a molecule like ozone has multiple structures that fit its description. So both of these structures are valid structures. And the only difference you can see here are the double bond and the single bond are switched. Now, the thing with resonance structures is ozone experiences this thing called resonance where it can be a hybrid of both of these structures, meaning the resonance hybrid that forms is a mixture of these two structures. So when I draw that, I'm going to draw that right here. So this resonance hybrid shows that it's actually a mixture of these resonance structures, meaning that the electrons are sort of balanced between the sides. Now, what I'm also saying is the polarity doesn't change. As we see here, this is still positive, this is still negative, this is still a bent molecule. It's just that the electrons are distributed more evenly. And as a refresher, if you see an arrow like this, I'm gonna write it. It shows that it's going from positive to negative for polarity. Now, a trick question a lot of people may ask you, let's say for ozone, they may ask you, how many double bonds are in ozone? And as you see here, if we're just thinking about ozone, when we see ozone in the atmosphere, ozone is going to be like this resonance hybrid, so it won't actually have a double bond or a single bond. It's actually between 1 and 2, so around 1.5. But that doesn't mean resonance structures can't be differentiated. There are certain resonance structures that are more stable than others. And the way to basically define which one is more stable is through formal charge. So we look at this molecule NCO minus. It has 3 resonance structures. These arrows indicate that these are undergoing resonance. So the way to sort of determine which structure is the most favored is through formal charge, like I said before. So there are 3 rules to essentially state which one's more stable. So the first rule is that all the formal charges have to be as close to 0 as possible. The second rule is that the most negative formal charge should correspond with the most electronegative atom. So in this case, that's oxygen. And the most electropositive is carbon. Now these have a hierarchy. So if a certain structure follows the second and third rule, but it isn't as close to 0 as something else that still follows these rules, then the one that's closer to 0 will be the more stable one. So let's start determining formal charge. If you guys don't know how to do formal charge, you should just check the website. I'm just going to do it really quick here. So this is a formal charge of 0, 0. That's supposed to be 6. Oops. But that's supposed to be -1. That's supposed to be 1, 0, 0. And this is supposed to be 0, +1, -2. So we have the first step is to determine all the formal charges, which we've done. So now let's check which one's closest to 0. These two are already the closest to 0, so let's look at these two first. So the most negative formal charge, okay, corresponds to the most electronegative atom, and that's true. Now it doesn't matter that the most positive formal charge corresponds to carbon because there are no other positive formal charges. So this actually looks good. Let's look at this one. So they're all close to 0, right? But we see that a -1 formal charge is corresponding to nitrogen, which isn't the most electronegative atom. So I'm not liking this one. The same thing with this one. This one's actually worse because a +1 shouldn't go to the oxygen because it's the most electronegative, and these aren't very close to 0. So this is definitely wrong. So we see that this option is the most stable.